Welcome to our lecture today. We are going to explore the exciting world of the special theory of relativity. We will focus on important ideas like the Lorentz transformation and its counterpart, the inverse Lorentz transformation. These key principles help us understand amazing things like length contraction and time dilation. Let us consider two inertial reference frames, S and S prime, with parallel corresponding axes such that they overlap at t is equal to 0. In the figure, you can see two reference frames with parallel axes such that they overlap initially at t is equal to 0. The frame S dash is moving with constant speed v with respect to S along the common x and x dash axis. Here it is important to note that in special theory of relativity, we always consider inertial reference frames. That means the reference frame which are either at rest or moving with constant velocity. Therefore, the relative velocity v between the two frames is always constant. The frames are never accelerated. Let us consider an event occurring at point P. The position and time coordinates of this event as measured by S frame are x, y, z and t, whereas the position and time coordinate of the same event as measured from S dash frame would be x dash, y dash, z dash and t dash. Now the question arises, how these two observations are related to each other? Answer to this question is Lorentz transformation or inverse Lorentz transformation. We apply Lorentz transformation when we have the coordinates from the S frame, that is, we know x, y, z and t, but we do not know the coordinates from the S dash frame, that is x dash, y dash, z dash and t dash are unknown. The unknown coordinates of the S dash frame are given in terms of known coordinates of the S frame through the four relations of Lorentz transformation given as x dash is equal to x minus vt over under root 1 minus v square by c square, y dash is equal to y, z dash is equal to z, and t dash is equal to t minus xv upon c square over under root 1 minus v square by c square, where c is the speed of light and v is the relative speed of one reference frame with respect to the other, and v should be comparable to the speed of light for Lorentz transformation to take effect. Otherwise, if v is much less than the speed of light, then Lorentz transformation will reduce to the Galilean transformation. To avoid any confusion in future, we should also notice that dimension of Vt is that of length, so that's why Vt is subtracted from x. Similarly, dimension of xv upon c square is of time, that's why it is subtracted from time. 1 minus v square by c square is dimensionless. Now I would like to highlight a very important point which many students does not notice in their casual reading, that v is the relative speed of one reference frame with respect to the other. Therefore, it is irrelevant that how this relative speed is arrived. It can be either way, like S frame could be at rest and S dash frame could be moving in the right direction with constant speed v, or S dash frame at rest and S frame moving towards left with constant speed v, or equivalently both the frames are moving in opposite direction with speed v by 2. So in all these cases, what matters is the relative speed between the frames, which is v in all cases, and this v is represented in the formula. Now, from our understanding of Lorentz transformation, we can very easily understand its counterpart, that is inverse Lorentz transformation. For Lorentz transformation, you are sitting on the S frame, knowing the coordinates x, y, z and t, and want to calculate the coordinates with respect to S dash frame, which is moving with constant speed v, with respect to u. On the other hand, for the case of inverse Lorentz transformation, Now you have shifted to the S dash frame. So now you know the primed coordinate x dash, y dash, z dash and t dash and want to calculate the unprimed coordinates with respect to S frame, which is moving with constant speed minus v, because this is going towards the negative x direction. Because as you are shifted to the S dash frame, the S dash frame will appear raised to you and the S frame will appear going in the opposite direction with the relative speed v. So what you have to basically do is to interchange the corresponding primed and unprimed coordinate and replace v by minus v, and with this operation into the formula of Lorentz transformation, you will get the formula for inverse Lorentz transformation. So, in this lecture, we have studied Lorentz transformation and inverse Lorentz transformation, which are very important to understand a special theory of relativity. Although I have not derived the result, which we do it in a separate lecture if you ask me to do so, but here I have tried to present a clear picture of the transformations so that you may start developing the understanding of the interesting world of relativity. Several other relativistic phenomena such as length contraction, time dilation, relativistic velocity addition, etc. are based on Lorentz transformation and inverse Lorentz transformation, which I will present one by one in the coming lectures. Hope you are enjoying it. Thanks.